Okay, let's unpack this. Predicting the economy is, well, it's notoriously difficult, right?
Yeah, absolutely.
Especially something as critical and frankly personal as the unemployment rate.
Yeah.
It affects everything, jobs, policies, our whole sense of stability.
Hmm.
Getting a clear, fast picture of something this dynamic, it's a huge challenge.
It really is. And traditionally, we've relied on macroeconomic data that, while it's essential, it definitely comes with built-in challenges.
Like what specifically?
Well, it's often incredibly complex, high dimensional with tons of variables to track.
Okay.
Plus, it's released on a staggered schedule, so you're always kind of waiting for the next piece of the puzzle.
Right, you're looking backwards.
Exactly.
All right.
And sometimes there are even data quality issues.
Yeah.
So getting a truly real-time, crystal clear view, it's tough with just the traditional numbers.
So what if there was a different way? What if we could tap in these vast new kinds of data streams, big data, like what billions of people are searching for online every single day, and combine that with these incredibly powerful modern analytical tools?
Yeah, that's where machine learning comes in.
Right. This deep dive is all about how these non-traditional data sources, paired with these cutting-edge ML techniques, are, well, fundamentally changing the game in macro forecasting.
Especially for the labor market.
Exactly. We've been given a stack of really fascinating research papers and notes exploring this exciting new frontier.
Mm-hmm.
They really dig into using these novel data streams and sophisticated models with a particular focus on unemployment forecasts.
Okay, so our mission for this deep dive is to cut through some of the technical stuff in these sources.
Yeah, you can get dense.
Figure out how these new methods and data actually work, see what they tell us about forecasting things like the unemployment rate, other economic signals,
Right.
and ultimately understand why any of this matters to you, our listener. What's the practical takeaway here?
Definitely. And while some of the sources do get into the nitty-gritty, mentioning formulas and Greek letters.
Just so slightly. Yeah, saw those. Our goal here is really to pull out the core ideas, make them clear, make them accessible, and keep it engaging. Think of us as your guides through this complex landscape.
Right. Sounds good. Let's jump right into it then. We start with the promise of alternative data, right? Data that economists maybe didn't traditionally use.
Mm-hmm.
And one of the most accessible and maybe most intuitive examples is Google Trends.
Yeah, Google Trends, it gives you this index basically ranging from 0 to 100.
Oh.
And it shows the relative popularity of a specific search term over time and also in particular locations.
So 100 is peak popularity.
Relative peak popularity for that term in that time frame, yeah. A value closer to 100 means it was searched for more often compared to its highest point. It's based on a big sample of all Google search data, so it kind of gives you a pulse on collective online interest in something.
So why is this potentially like gold for economics, especially unemployment?
Well, the simple idea, the intuition, is that when people become unemployed, or maybe even just fear they might be, where do they often turn first these days?
The internet, Google.
Exactly. They start searching online for things related to that situation, job openings, unemployment benefits, you name it.
Right. And the early research latched onto this pretty quickly, didn't it? Looking at using Google Trends for forecasting the U.S. unemployment rate.
They did. But here's where the first challenge pops up. And it's a really important practical insight from the research.
Okay.
Choosing the right keyword is crucial. And it's surprisingly tricky.
Tricky? How so? Wouldn't you just search for, I don't know, unemployment?
Well, you could, but think about it, just using a broad term like unemployment might capture all sorts of searches.
Like students doing homework.
Exactly, or people looking for general info, or even people who already have jobs but are maybe looking for new ones.
Okay.
You need keywords that really reflect the search intent of someone actively facing job loss or threatened by it or trying to navigate that specific situation.
So you need to filter out the noise.
Precisely. And crucially, you need to separate that signal from searches by people who are just browsing job listings while still employed. Finding those specific digital breadcrumbs, the ones left by people whose economic status is actually changing, that takes careful thought and a lot of testing.
That makes total sense.
Yeah.
Finding the signal within all that noise. So the sources talk about using the daily Google Trends data because it's so fast,
Very timely.
or something called nowcasting.
Right. Estimating what's happening right now before the official data comes out, maybe weeks later.
And even backcasting, estimating past conditions.
Yeah, specifically for things like the weekly unemployment insurance initial claims in the U.S. trying to get a faster read on those numbers.
And what's the key takeaway? Does it work?
What's fascinating here, and a really key finding in the research, is that when you incorporate this Google Trends data into the forecasting models, it can provide statistically and economically significant improvements in those nowcasts for U.S. government employment data.
Okay, break that down. Statistically significant.
Good question. It basically means the improvement in accuracy isn't just random luck. The statistical tests they run show there's a very high probability that this improvement is real, it's repeatable.
Got it. And economically significant.
That means the improvement is actually large enough to matter for making decisions. It's not just a tiny tweak. This includes nowcasts for really widely watched data like revisions to non-farm payrolls, the NFP numbers.
Wow.
So it adds timeliness and accuracy. And interestingly, this improvement was even noted for specific sectors, like searches related to architecture and engineering jobs seemed particularly useful.
Suggesting that data might be better suited for tracking certain parts of the economy.
Potentially, yeah. It gives a more granular view sometimes.
So tapping into this real-time search data makes the official numbers potentially more accurate and definitely available faster. That sounds like a big deal.
It is a big deal. And it's not just unemployment either. The sources mention using it beyond the labor market.
Oh, yeah. Like what?
Like nowcasting GDP growth. There's an OECD weekly tracker project mentioned that specifically uses Google Trends as one of its inputs to get a faster read on overall economic activity.
Interesting. But okay, it's probably not as simple as just downloading the data and plugging it in, right?
No, definitely not. It requires pre-processing. That's crucial.
Why is that?
Well, because the index is based on samples and it can be sensitive to recent periods, you can run into issues. Things like long-term bias creeping in or sampling variance noise from the fact it's a sample.
So you have to clean it up first.
You have to clean and shape the data properly before you feed it into any kind of model.
Absolutely.
And speaking of models, what kinds are used with this data? The sources mention some specialized techniques.
Yeah, because you're often mixing data frequencies, right?
Yeah.
Daily searches with monthly reports.
Right.
So one type mentioned is MIDAS regression models. MIDAS stands for mixed frequency data sampling.
They're specifically designed to handle that challenge combining data that comes out at different speeds. They also mention things like semi-parametric estimation procedures.
Oh, sure.
Sort of a hybrid approach. They combine aspects of simpler, more rigid models with more flexible, data-driven methods, often used with this kind of internet search data.
Okay, so we've got this new kind of data available super quickly. But to really squeeze the most value out of it, especially if you have potentially thousands of search terms or other variables floating around.
Yeah, it gets complex fast.
You probably need more powerful tools than the old school linear statistical methods.
Exactly. And that's where machine learning really enters the picture properly.
Right. Why do those traditional linear methods often fall short here?
Well, you kind of hinted at it earlier.
The real world isn't always a straight line.
Exactly. Complex economic data, these huge alternative data sets, they often have nonlinear relationships between variables, meaning the relationship isn't a simple one-to-one proportion. How unemployment affects spending might change, depending on how high unemployment is, for instance.
Okay.
Or the data is very high-dimensional, tons of potential predictors relative to how many historical data points you have. Traditional linear models make pretty rigid assumptions about these relationships that just might not hold true in the real world.
They're too simple sometimes.
They can be.
Huh.
ML methods, on the other hand, are often much better at handling these nonlinearities and high dimensions without needing as many restrictive assumptions about how the data should behave. They can find patterns a simple linear model would completely miss.
Okay, so what kind of ML models are we talking about? The sources list a few names that sound a bit intimidating.
Chuckles. Yeah, the names can be jargony. Let's break them down conceptually. The sources highlight a few key categories. First up, shrinkage or regularization models.
Shrinkage.
Yeah, think of methods like lasso, elastic net, ridge regression. These are really useful when you have a lot of potential predictors, maybe hundreds of Google search terms, other data streams.
Like trying to find the few important needles in a giant haystack of data.
That's a perfect analogy. They work by adding a penalty during the model estimation process. This penalty essentially shrinks the estimated importance of some variables towards zero.
Okay.
Now, for lasso and elastic net, this can even shrink some parameters exactly to zero.
Ah, so it kicks out the irrelevant stuff.
Exactly. It effectively performs variable selection. It helps the model ignore the noise, ignore the irrelevant variables, and focus only on the ones that are truly important for making the forecast.
And that helps avoid overfitting.
Precisely. Overfitting is when your model learns the past data, including all its noise, too perfectly.
So it looks great on historical data.
But fails miserably at predicting the future because it learned noise, not signal. Shrinkage helps prevent that, helping you build a model that generalizes better.
Okay, so they help find the key signals and build a more robust forecast. Makes sense? What's next?
Then you have nonlinear models. Examples mentioned include support vector regression, SVR, artificial neural networks, ANNs, and random forests.
ANNs, it's like AI stuff, right?
Yeah, you hear about them a lot in AI, things like multi-layer perceptrons. They're noted particularly for their ability to handle really complex nonlinear data patterns. And interestingly, the sources note they can sometimes still generate useful output even if parts of the input data are missing or maybe inadequate.
Resilient.
Somewhat, yeah. And random forests and support vector regression have also shown really strong performance in macro forecasting applications discussed in these papers. They're good at capturing complex patterns.
What's the basic idea behind a random forest? Sounds woodsy. Chuckles.
Hey.
Think of it like assembling a forecasting committee, but with decision trees.
Okay.
A random forest builds a whole bunch of individual decision tree models. Each tree looks at the data slightly differently, maybe using a random subset of predictors or data points. So they each have a different perspective.
Exactly. And then the random forest combines their individual forecasts, often just by averaging them or taking a majority vote. By aggregating the wisdom of many diverse trees, it tends to be much more robust and accurate than any single tree or even simpler models could be.
Okay, that makes sense. Like the wisdom of the crowd, but for forecasting models. Very cool. Are there ML models specifically built for macroeconomics, given its unique challenges like time series data?
Yes, absolutely. The sources mention specialized macro ML models. A key one is macroeconomic random forests, or MRF.
Ah, building on the random forest idea.
Exactly, including variations like autoregressive random forest, ARRF, and factor-augmented ARRF. These are specifically adapted for macroeconomic time series data.
How are they different?
They're designed to capture complex, time-varying relationships, how the influence of different factors, say, consumer confidence versus interest rates, might change over the course of the business cycle.
That sounds really powerful. Does the research show they actually work better?
Yes, a key finding highlighted is that these MRFs show significant gains over traditional autoregressive models, which are like the workhorse standard in time series forecasting. And they seem to have performed particularly well, specifically in forecasting economic downturns like the 2008 recession.
Wow.
What's really fascinating here is they don't just give a better forecast number. They can actually reveal how the importance or contribution of different forward-looking variables, maybe financial indicators, certain sentiment measures, changes significantly before a recession actually hits.
So they flag the warning signs.
They essentially highlight the early warning signals that the model is picking up within the data. It gives you a peek under the hood.
That's incredibly insightful. It's not just predicting what, but offering clues about why. Adds a whole layer of understanding.
It really does. And the sources are clear that these various ML models, the shrinkage ones, the nonlinear ones, the specialized macro ones, they can be used individually, sure, but often for the best results, they're combined in various ways.
Which leads us perfectly to the next point, where the real power seemed to lie, putting machine learning and these alternative data sources to work together.
Yes. This is where you really see the most significant improvements highlighted in the research papers.
So.
Using ML models, whether they're linear models fitted with lasso or elastic net to handle all those variables, or complex nonlinear ones like ANNs to capture tricky relationships, using those alongside daily Google Trends data, has been shown to significantly improve forecasts of things like weekly unemployment initial claims compared to just using the traditional macro and financial predictors alone.
So a combination really is greater than the sum of its parts, the data plus the smart tools.
Precisely. The timelier alternative data provides the new, maybe previously unseen, signal, and the ML techniques are powerful enough to actually extract that signal effectively, even when it's buried in noisy, high-dimensional sources.
Got it.
And for specific U.S. employment data, like those non-farm payroll revisions we mentioned,
NFP numbers, yeah.
using ML techniques like random forest and ElasticNet provides a substantial and statistically significant improvement over traditional linear regression methods, specifically when that Google search data is included in the mix. The search data adds real value when processed smartly.
Okay. The sources also bring up another approach, combining factor models with shrinkage methods as a way to mine big data. Can you explain what that entails in simple terms?
Absolutely. Imagine you have just a gigantic data set, maybe hundreds or thousands of variables.
Okay.
It could be tons of different Google search terms, maybe data from credit card transactions, satellite imagery, online job postings, all sorts of things.
But the big data.
A factor model techniques like principal components analysis, PCA, independent component analysis, ICA, or sparse PCA, SPCA, is used to basically distill all that massive information down into a smaller, more manageable set of underlying factors.
So it summarizes the main trends.
Exactly. Think of these factors as capturing the main patterns or the common drivers moving across all those thousands of individual variables. It reduces the sheer dimensionality while hopefully keeping the most important information.
Okay, so you boil down the big data into key themes or factors. Then what?
Then you take these extracted factors and you combine them with those shrinkage techniques we talked about, Ridge, Lasso, ElasticNet, within your forecasting models.
So you apply the smart variable selection to the factors.
Essentially, yes. You're building a forecast based on these distilled signals. And the research suggests that the more sophisticated factor methods, like ICA and SPCA, when coupled with shrinkage, can often outperform simpler approaches.
Why is that?
They seem to be better at separating out the distinct underlying signals and, again, preventing the model from just overfitting to the sheer volume of raw data.
So it's a two-step process. First, distill the vast big data into key, clean signals, which are the factors, and then use smart ML methods like shrinkage to build a robust forecast based on those signals.
Yes, that's a great way to put it. It's about smart dimensionality reduction, followed by smart modeling.
Okay. The sources also mention ensemble techniques, like bagging and boosting.
Right. These methods take the idea of combining models even further.
How do they work?
They typically build multiple individual models. Sometimes these are called weak learners, meaning they might not be fantastic predictors on their own.
Okay.
But then the ensemble method cleverly combines the outputs from all these weak learners, maybe through averaging, or more complex weighting schemes, to produce a final prediction that's often much more accurate and stable than any single model could achieve on its own.
So again, leveraging diversity.
Exactly. Bagging and boosting are different ways of creating and combining those diverse models. Bayesian model averaging is another related method mentioned, which combines forecasts from different models by weighting them based on how well they seem to perform.
It sounds like they're really throwing a lot of different approaches at the problem and combining the strengths.
That's a good summary. Leveraging the strengths of multiple models or diverse approaches. And importantly, the application here goes beyond just forecasting the overall unemployment rate.
Oh, yeah.
MLs is also being used to predict something really critical for individuals and for policymakers: unemployment duration.
How long someone is likely to be unemployed once they lose their job.
Exactly, which is a huge factor in people's lives and in designing effective support programs.
Absolutely. So what helps predict duration, according to these ML models?
The sources highlight some important factors identified using these techniques. They mention ensemble models, specifically one called boosted She-H-Aid. That's a kind of decision tree-based model.
Okay.
And also discriminant analysis, which is a statistical technique often used for classification, like predicting which duration category someone might fall into.
And what did they find?
Key predictors include things you might expect, but the models help quantify their importance. A job seeker's unemployment history is big, like previous spells of unemployment, or how long it's been since their last job.
Makes sense.
Also, age, education level, location, regional differences matter in gender. The sources specifically note that cumulative unemployment history and the number of days since the last occupation seem particularly strong predictors for how long someone might remain unemployed.
That makes intuitive sense, doesn't it? Your past experience, how recently you were working, that would strongly influence how quickly you might find a new job.
Right. And the ML models help formally identify and weigh these factors. And just to broaden the scope a bit more, these ML methods aren't just for unemployment. They're being applied to forecast other related economic and financial concepts where the labor market plays a role.
Such as?
Well, one example is using deep learning for forecasting mortgage risk.
Like predicting who might default.
Exactly. Looking at things like prepayment risk and delinquency risk. Deep learning models, which are these complex networks with many layers, are particularly good at finding intricate, non-obvious patterns in huge data sets.
And unemployment data feeds into that.
Yes, variables like state-level unemployment rates are influential factors in these mortgage risk models. ML helps uncover and model the complex, often nonlinear interactions. For instance, how a low FICO score combined with a large loan balance and rising local unemployment significantly increases delinquency risk, much more than just looking at each factor in isolation.
It captures the combined effect.
Right, it models the interaction. ML can also enhance volatility forecasting in financial markets, which is obviously crucial for investors and policymakers trying to navigate choppy waters, especially during recessions when volatility often spikes.
Okay, wow. So we have this new data coming in fast. We have these incredibly powerful tools to analyze it, and they're being combined in really sophisticated ways, forecasting everything from unemployment rates to how long someone might be out of work, even predicting financial risks.
Yeah, it's a broad application.
How do the researchers actually figure out if any of this works better than the old ways? How do they, evaluate these forecasts, keep score?
Yeah, that's critical. They use common statistical metrics to measure success. One frequently mentioned in the sources is root mean squared error, or RMSE.
RMSE. What does that tell you?
It essentially quantifies the average size of the forecast errors. It tells you, on average, how far off the predictions were from the actual outcomes. Importantly, it penalizes larger errors more heavily than small ones.
So lower RMSE is better.
Lower RMSE means a more accurate forecast, yes. Fewer, smaller errors on average.
And they don't just eyeball the RMSE numbers and say, hey, this looks better, right? They use formal tests.
Correct. They use formal statistical tests to compare the predictive accuracy of different models rigorously. The Diebold-Mariano test is one such test commonly mentioned in these studies.
And what does that do?
It allows researchers to statistically determine if one model's forecasts are significantly more accurate than another's, meaning the difference in accuracy isn't likely just due to random chance or the specific data sample they happen to use.
So it adds statistical confidence.
Exactly, and studies using these tests, as reported in the sources, have repeatedly shown that these newer methods, the ones combining alternative data like Google Trends with ML techniques, provide statistically significant improvements in forecasting accuracy compared to the more traditional approaches.
So these improvements aren't just marginal or, anecdotal. They actually hold up under rigorous statistical scrutiny. They represent meaningful enhancements to our forecasting ability.
That's right. The evidence suggests they represent a tangible step forward in accuracy and timeliness.
Which brings us right back to the crucial question. Why should you, our listener, care about all this, complex data wrangling and machine learning? What's the relevance here?
Well, these technical advancements really do have real-world implications for potentially everyone. Better macroeconomic forecasts, especially for something as fundamental as the labor market.
Yeah.
They provide more timely and more accurate information. This higher resolution picture can inform crucial decisions.
Decisions made by who?
By governments, say, deciding on stimulus packages or support programs. By businesses planning hiring or maybe expansion. By central banks setting monetary policy, like interest rates.
Okay.
Better forecasts can contribute to better timed policy responses, help businesses plan more effectively when things are uncertain, and potentially even impact financial markets by reducing some of that uncertainty.
So it's about helping the big players, government, business, central banks, make smarter, faster moves, which can then ripple out and affect the stability and growth of the whole economy that impacts all of us.
Exactly. It's about potentially better overall economic management. And maybe on a more individual level.
Yeah.
Understanding unemployment dynamics better, including how to predict duration more accurately, or seeing how unemployment links to financial risks like mortgage defaults.
Yeah.
That provides valuable insights too.
For individuals.
Well, obviously for policymakers managing systemic risk, but potentially also for individuals. Perhaps when making decisions about financial planning, saving strategies, maybe even career path choices depending on regional economic forecasts, it adds another layer of information.
This deep dive really shows how accessing and analyzing these vast new types of data with powerful computational tools like machine learning isn't just some academic exercise.
No, it's very practical.
It's creating a more nuanced, more real-time understanding of the economy than we've ever really had before. It's like seeing the economy not just through quarterly reports that lag, but through this constantly updating, wider, higher resolution lens that's made possible by all this digital activity.
It truly is an evolution in how we can approach and maybe solve complex economic problems, moving towards a much more data-driven understanding.
So to wrap up this deep dive then, the main takeaway seems pretty clear. The combination of alternative data sources, especially timely signals like Google Trends and sophisticated machine learning techniques, it's proving to be a powerful evolution in macroeconomic forecasting.
A real step change.
It's offering timelier and, according to the research, significantly more accurate predictions of key indicators like the unemployment rate, and revealing deeper insights into economic dynamics along the way.
And our mission here, hopefully, was to give you a shortcut to understanding this exciting new frontier, highlighting the specific data sources, the kinds of ML techniques being used, and some of the concrete empirical findings coming out of recent research, all without getting totally bogged down in the equation.
Right. Which leaves us with maybe a final thought for you, the listener, to consider as you go about your day.
Okay.
If internet search data, just those digital breadcrumbs left by people's curiosity and their circumstances, if that can help predict joblessness or track broader economic activity, what other digital signals, or maybe even previously overlooked data sets entirely, might contain valuable, untapped insights about the economy or society that we haven't even thought to look at yet?
Interesting question.
And how could leveraging those potentially change our collective ability to understand and navigate the world around us in the future?
It certainly opens up a vast landscape for further curiosity and definitely exploration. Lots more data out there.
Absolutely. Thanks for joining us on this deep dive. Stay curious.